Okay, so we will wait for 2 or 3 minutes, and then we can start discussing this all those live sessions that we are gonna operate. Is my screen visible to you guys? Okay, great, great, great. Okay, then it's 6:05. We can start, right? Katagata? Okay, okay, yeah, great. Yeah. So, good evening, everyone. As you have all known, today we gathered to for this live sessions for this NPTEL course, Basic Thermodynamics, Classical and Statistical Approaches, which course ID is NOC 23 CY07, and Professor Arnab Mukherjee is the instructor. He is from IIT Pune, and this is the sort of a assignment solving session or some kind of problem solving session. This is the first week, and I am Dibyendu. I will help you guys to learn about those things to solve those problems. And I'm a Prime Minister Research Fellow at the Department of Physics of IIT Kanpur, and I'm doing my research in soft and active matter research, and primarily I'm focusing on studying bacterial dynamics in different kind of geometries, potentials, and this kind of stuff. You can check my website that I will come to later. Okay. So okay, so before we start the next problem solving and the learning process, it would always be useful to to set some guidelines or set some announcements so that you can follow all those things in a tangible manner. So every Tuesday we are gonna have our live session 6 p.m. to 8 p.m. for 12 weeks. That is like the duration of this course, and these sessions will be for around 2 hours. Maybe sometimes it will be more than 2 hours. Sometimes it will little less than 2 hours. And one thing, this since it is in online session, so sometimes it can happen that there's some kind of technical issues. Google Meet might stop, so you can join within few minutes and within same link that I have, that actually I think has been shared with you guys. And you guys can call me Dibyendu. Please call by my name. I'm pretty uncomfortable if you call me by sir. So please call me by my name. And these sessions, and pretty one good announcement, these sessions will be recorded, and is something like this. Can you guys see some marking on the screen? Yeah, yeah, yeah. So these sessions will be recorded, and this link of the video will be shared later. Okay, and of course, since it's a learning sessions, if you guys can have some questions or many questions or lot of questions, please feel free to interrupt me at any point of time. Please unmute yourself, and while I am talking, if you guys can mute yourself so that there will be a good way of communicating with each other. And if you cannot do this, like if you cannot unmute yourself, some kind of problem, you can leave your message in the chat box, and I will be constantly monitoring that, and I can check that later, or check them momentarily after like 10 or 15 seconds later, or 1 minute, 5 minutes later, and I will try to solve that. And at last, congratulate everyone for taking this journey to learn about this perplexing field of science, which is thermodynamics. And we will talk about the problems and try to solve those problems. But if time permits, I can share some stories of this evolution of these fields, thermodynamics. And you can follow me. This is my website link. Okay, any questions so far? Any comments or questions? Yeah. Okay. So ideally, it should be sent to you guys by tomorrow morning or tomorrow night. But let's say I will record this. I'll send this to NPTEL, some kind of communication. This thing can take 1 or 2 days. So I will recommend you to like wait for 1 or 2 days, and probably that would be, I think that would be ideal, snoozing period of 1 or 2 days. But this is, since this is the first week, sometimes like we guys are not comfortable with this kind of recording or 2 hours long, and some kind of problems may happen. So for first week, just just some delay may happen, so that's the thing. So okay, okay, okay. So any other comments or any other expectations that you have for this course, for this session? You can please comment on that. Okay, so Okay, okay, so great, it's great, great. Okay, so we will learn about those things, and also I think personally, I think the history of thermodynamics is also very important. So probably we will explore those fields. Okay, okay. So let's just jump into the first problem. Okay, okay. So this is a sample problem. These are the problems for the previous year's assignments. So the problem says there are three stones: A, B, C, which are in thermal equilibrium with each other, and the temperature of stone A is 30 degrees centigrade. So the question is, what will be the temperature of B? So we can easily, after learning about the first week lessons, we can easily say that it is some like 30 degrees centigrade. But since you have promptly said that we want to explore more, so can you say, can you tell me, Tothagato, what is or what are the basic laws that can support this answer, that 30 degrees centigrade? What? Yeah, yeah, yeah. Great, great, great. Yeah, Zeroth law of thermodynamics. So we will just first explore what is Zeroth law of thermodynamics. So some Zeroth law of, okay. So the statement is like that. Let's say there are three objects or three systems, A, B, and C. If C, let's say, it is better to state the statement by saying this. It will be good. Let's say if a body C, which is in thermal equilibrium with two other bodies A and B, then we can say that A and B are in thermal equilibrium. Tathagata, can you comment on that? Is the law complete, or is the statement complete? Okay, that's a good point, but we will come to that later. But it is quite intuitive, right? A system is in thermal equilibrium with itself, right? Yeah, it is quite intuitive, but it can. But if you rigorously say a law, sometimes it can happen that a system can there is a, property that assigns that feature, that system is in thermal equilibrium with itself. But before stating that law, we sometimes forget to mention that this zeroth law of thermodynamics, before stating that, we have to mention that system C is, and system A and system B, they are they are in thermal equilibrium with itself. That is a common thing that we actually forget. So this thing, this a system which is in thermal equilibrium with itself, this is called a, there is a name. Let's see. Okay, so system. Okay, okay, okay. Example of system is in thermal equilibrium with itself. This property is called reflexive property. From the, I'm trying to sorry. Okay, so these are the logics from geometry and from, from a logical point of view, because you have probably learned about this transitivity, additive properties, and these kind of properties in your school days, right? Yeah, yes, sir. So probably this reflex. Have you heard about this reflexive property? Okay, so yeah, great. So a system, when it is in thermal equilibrium with itself, and it is that property is called reflexive property. Now you can say it's very intuitive, but let's say a system is there, okay, and you subdivided those system in different subparts, okay, and we can say that these are in thermal equilibrium if these subparts, they have that common, that common variable that we haven't mentioned yet. It can be temperature, it can be any other thing. We won't mention right now. If this smaller parts have the same assigned variable or same tagged thing, then we can say these are in thermal equilibrium. So reflexive property says that when we can subdivide it, subdivide the system into different parts, and also that property that is assigning that system is similar into that subgroup, is same, then we can say the system is in thermal equilibrium with itself. Okay. No. Yeah, it's in macroscopic system. It's macroscopic system right now in Zeroth. Like, okay, just go into this thing. Zeroth law of thermodynamics never talks about the concept of temperature from microscopic point of view. That you have probably understood, right? Because whenever we are seeing that three systems are there and they have their macroscopic observables, or some observables are similar for every other system, then we can say they are in thermal equilibrium. So whenever we are talking about zeroth law of thermodynamics, we are talking about from, macroscopic point of view. So from, if we want to talk about microscopic point of view, then we have to talk about like their kinetic theory in that kind of perspective. So then each and every constituents of that system for molecules, we have to take into our consideration all the degrees of freedom for all those particles of all those, constituents together. Yeah. So is it clear? Yeah. So so this is so now then, if I can if I can take this into a quoted message, then we can see that before stating the zeroth law of thermodynamics, we have to assign that system should be it should be in thermal equilibrium with itself first, and which is called reflexive property. So that is one thing. So we will come into details of this zeroth law because there are more problems regarding zeroth law. So one by one, I will explore all those. We will explore together the zeroth law of thermodynamics. Okay. Okay. So since I stated the law, so that would be this temperature of B will be this 30 degree. Okay. Okay. Now comes one thing. So here says the zeroth law of thermodynamics introduces the concept of a blank. This blank is heat or temperature or work or none of the above? So you probably know the answer, right? This is temperature. Macroscopically, this is temperature. Okay, this is temperature. So this is quite some, statement kind of thing. Let's dip more into, as I've said in the previous slide. Let's dive more into uh, the details of zeroth law. So zeroth law also uh, talks about one thing, which is so this measuring the thermal equilibrium properties of three different systems also takes into account one other hidden logic, which is called Euclidean relations. Sorry. Okay. So what does this Euclidean relation uh, tell? It tells that actually whenever a statement uh, holds these Euclidean relations, that says that actually holds the axiom one of the Euclid's elements, and that axiom one of Euclid elements states like this. Sorry. Okay. So what does it say? It says that magnitudes which are equal to the same are equal to each other. That means just dive deep into the statement. So we are assigning some value to a variable. Okay, we are talking about some value of a variable, and they are same in magnitude for two systems. Then we can say they are equal to each other. Just try think about the logic of this statement. Tothagato. Okay. Yeah. So the magnitude means some scalar quantity, right? So some kind of measure of that property, which are equal to the same means same system are equal to each other. So that is actually related to our zeroth law of thermodynamics, right? In zeroth law, we talk about that kind of logic. Yes. Because right now we are talking about the philosophy and the logic of the statements. Because zeroth law of thermodynamics is very crucial. Do you know why it is? Let's discuss about this thing. Okay. Do you know why it is called zeroth law of thermodynamics? Okay, maintain the sequence. Okay. Yes. Quite right about it. So first, second, and third law were pretty earlier before this zeroth law, and so we couldn't put this as a like first, second, third, and fourth. So that's why we have to put it before first, second, third, and that's why zero law of thermodynamics. Okay. 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 Yes, yes, yes. So this is okay. So Euclidean geometry is you know that Euclid was a philosopher, right? Okay, so Euclidean geometry, based on that philosophy or logic or set axioms of Euclid's elements. Yes. Yeah. Yeah. Exactly. Exactly. I'm happy that you are appreciating that invention, because back then it's quite, right now it's quite intuitive, but back then it was not. Yeah. Yeah. So okay. Okay. So that's why these relations also hold. So this zeroth law also hold Euclidean relation. So I want to actually dive deep into the statement and try to prove actually why this, because sometimes it says that zeroth law of thermodynamics talks about equivalence, right? Yeah, that is why I'm coming. Okay, that is why I'm coming. Okay, so now when we are comparing two objects, so okay, when we are comparing two objects, we can actually assign some binary operation between these two, right? Okay, so you know about in your basics in your school days that there are some binary operations between two elements, between two sets. Exactly the same thing. The properties will be assigned in that system A and that system B, and you are comparing or you are doing some operations with those two systems. Okay, so in mathematics, sorry, a binary relation that are reflexive, and so it was reflexive at I already said about it. It was reflexive, and later we got to know that it is also, sorry, Euclidean, then that, sorry. Okay, so try to understand this thing. Okay, so what does it say? It says that in mathematics, a binary relation that are reflexive and Euclidean, then that relation is equivalence relation. So in your school days, you know about equivalence relations, right? So if two set are there, two elements in the set are there, and or let's say two set, and they are equivalent. we can say that we can map those elements in those two systems together, because this is also quite important, right? Equivalence, because you cannot say that you know uh, let's say mangoes are equivalent to oranges. Exactly, so you cannot say that like that. That is also important here. So I'm trying to establish these things, and from a basic point of view, some basic logic point of view, because as you probably will know about these things in your later days, that this thermodynamics, and later you will not know about from statistical physics or statistical mechanics, then it involves a lot of mathematics. And these mathematics are not like some doing some integration, differentiation, this kind of thing. From depth of logic point of view, depth of debates, depth of some giving some strong argument. So that is quite important here. Okay. Okay. So so far you have any questions, or you just let's revisit these two things, or you just try to understand this thing in 1 minute. Just recapitulate this thing for 1 minute. I will come to this later. Okay. Okay, Tothagoto. So any questions? Okay. Nice. Okay, so reflexive in the previous. Okay, I'm just coming back to this. Okay, so this reflexive property. Okay, property. It's a simple statement, but it says, let's say there is one. Sorry, there is one system. Okay, A. It is actually is in thermal equilibrium with itself. From it is the statement that I have just given to you. It is from physical point of view, the statement. Let's say I said that this system A is in thermal equilibrium with itself, means it is in equilibrium. And what kind of equilibrium it is? Thermal. So some sort of a variable is there which assigns the system, which is assigned to the system, and that if we subdivided the system into different kind of compartments, for each and every compartments, that is similar, but not from a microscopic point of view. It's from a macroscopic point of view. Now you can say, let's say Dibyendu, there are 10 to the power 23 molecules. Is it same for all the molecules? No, we are not talking about the microscopic point of view. We are talking about macroscopic point of view. So here we will talk about volumes. Here we will talk about surface area. Here we will talk about, let's say, a 1D system from length. So from volume means this is a, sorry, Sorry. This is a cube. Let's say this is a surface, okay? And if let's say that variable t is for this whole system A, and these are the subdivided system, t is also same for this also, okay? This is what I meant. Same constituent. Exactly. Let's say that area of this whole surface is 10 meter square, and you have subdivided them in 2.5 meter square kind of a block, okay? And then this t is also same for all those portion. Yes, yes, yes. Yeah, that's right. Because remember one thing, this is sometimes we actually forget. This zeroth law of thermodynamics talks about from macroscopic point of view. Because here we never mentions we never mention, because the usefulness of zeroth law of thermodynamics is that it talks about temperature irrespective of talking about entropy. So that is one thing. It doesn't talk about entropy, but it is establishing temperature. So for zeroth law of thermodynamics point of view, it it is actually for macroscopic point of view, not for kinetic theory point of view, where you can actually talk about a single molecule. But in that 2.5 meter square, like now we can say in that 2.5, in this in this portion, there will be a millions or trillions of molecules, right? Gas molecules. So that, so we are assigning temperature T to all those molecules. That is the meaning of the macroscopic point of view. So you can ask me, uh, how can we know that there are different kind of, there are the molecules are distributed in that surface differently. So temperature may be different for that, but we are assigning, when we are calculating the velocity distributions or something like that, we are assigning temperature of the system is T, right? You have seen that, right? Yes. Temperature of the system is this. So that is called, that's why actually it is a macroscopic quantity or macroscopic variable, right? So when we will talk about P, V, T of a system, these are all macroscopic variables from thermodynamic point of view. Okay, so is it clear right now? A little bit. So this reflexive, this reflexive statement, it may sound very easy, but right now you can appreciate the depth of the statement, right? Hmm. Yeah. So some right now we cannot go to the deep mathematics of this, of these constituents, because this will be beyond the scope of this course, and this will be difficult also. So it would, so we will stop here and we'll try to learn more things about thermodynamics or zeroth law of thermodynamics in the next questions, okay? But I can actually, I can answer in your next classes if you have any other doubts to understand, or I can answer you in the remaining of the class if you have any doubt regarding this. Okay. Okay. So that's all. This is this. Okay. So okay. So these questions are like, there are n objects in thermal equilibrium, right? N objects in thermal equilibrium. Therefore, all the objects have the same amount of heat? That is the question, right? Now, all objects have the same amount of heat or not? Now, Tathagato, I have given you the full flavor of the Zeroth law of thermodynamics. Now you please uh, tell me the answer and logic behind that. We I am not interested in knowing the right answer of this thing. I want to, if you give a wrong answer, please justify that. Okay, that is my motto. Not my motto is like right knowing the correct answer. Obviously, the correct answer is there, and but knowing the actual logic or actual reason for that. That is the main reason. That is my main target or main. I will be happy if you do that. Okay, just tell me and give your logic. Yeah. Yeah, object identical, same size and all. Let's say they can have same identical or non-identical. Let's say make it general. They are not identical. Means they have different kind of volumes or some shapes. Let's say there are ice and there are water. Hello.
Yes.
So ice and water can be in thermal equilibrium.
Yes.
So they are the identical are the identical objects? Technically means you want to know about the H2 molecules, like the
Yes.
concept. But the states of the
Piece of this.
states are different. Let's say two liquid that would actually be good. Let's say there is glycerol and water. They are liquids. Okay, so they can be in thermal equilibrium, right?
Yeah.
They can be thermal equilibrium. Now say your answer and logic behind it. Hello. Now the reason for that. Yes. Bravo, bravo. Great, great. Yes. This will be false. Because zeroth law of thermodynamics says that when this A, B, C, D in number of in number of systems which are in thermal equilibrium, they have same temperature, right? They have same temperature, right? So they do not talk about are do they have same amount heat or not. That will depend, as you have rightly said, the mass, the specific heat. There are different kind of constituents. There are the properties of the material, different kind of thing. Because as you know, the specific heat of water is much larger, right?
Yes.
It can absorb, it can contain more. Specific heat means it can contain more heat for same amount of temperature compared to other lesser specific heat materials, right?
Yes, sir.
Yes. So that's the thing. So just for the completion, I will write the, because this should be the other students which are not here, for their it will be useful. False, because as Tothagat rightly said that zero, sorry, ze- zeroth law of thermodynamics tells temperature is, sorry, is same for objects in thermal equilibrium. Okay, okay. Now we'll go to the next. Okay, this is actually velocity. Let's come back this if there is it's velocity distribution. So here the zeroth law of thermodynamics is being, like, the discussions about that will we will stop here. But before, coming to an end for this zeroth law of thermodynamics, I want to say that in 19 in sorry in 1930s, this zeroth law of zeroth so- zeroth law of thermodynamics thermodynamics term actually est- established by Dr. Ralph H. Flower. Flower. Okay, so he has established the term, and as I probably the main actually message of this, that it talks about thermal equilibrium, which in return tells that temperature will be same. And also one important thing, it does talk about temperature without mentioning entropy. That is interesting part.
Yes,
Yes, yes. So okay, okay. So any question? We just think about these three problems, and for 1 minute or 2 minutes, if you have any other question regarding zeroth law of thermodynamics or any comments. It's all right, right? Okay, okay, okay. Now we are coming to the velocity or speed distributions or the collisions. Now we are probing deeper into the system, right? Because now when we are talking
yes,
about molecules, yes, we are probing deeper. So here the question says that I have a box which filled with O2 gas at temperature T. Okay, fine. My friend says that since the temperature is fixed, the velocity of each O2 gas molecule will be same. Is he right? Now, my friend Tothagata, what would you say? What is your, like, guess? Right or wrong, just like you have a basic understanding. Just from that perspective, you say. I will comment on that. Later, I will tell you the answer. Just well, say. Velocity means general velocity. It's moving, right? And you are measuring the displacement, and then think about it for 1 minute because we have enough time. Because we will go one by one. So think about it for 1 minute. Okay. Okay. Let's say gas is ideal. Hmm. But they are colliding with each other, right? They are colliding with each other. But the particle, but one particle, which is sometimes colliding very rapidly, maybe not colliding that rapidly at other point of time, right? It can so happen because this collision probability is varying. You agree to this point? So if that collision probability is varying, then how can you say that velocity or speed will be same? Okay, okay, you are saying it is not will not be same. Okay, so okay, yeah, yes, you're right. Mm, 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 mm. Yeah. So the logic of this point is like since they are colliding with different probabilities at different point of time, and that is also varying. So they do not have the same speed for each molecule. They have a distribution. They follow a distribution. We can say about the probability of that collision, and from probability of that collision, we can say that there will be a probability of distributions, and from that probability of distribution, we can get a distributions. Yes. So this will be no, no, no. Okay. So the reason for this, or distribution of velocity or speed. Okay, so now we will go to the next question. Here in this question, saying if somehow we stop all the collision between gas particles, will we still observe the? Hi Pranjal. Okay. Okay. So will we still observe the velocity distributions? So let's say the particles are colliding with each other, and we will somehow stop all the collisions. So velocity distribution, we will still observe the velocity distributions or not? Tosagato, your comment? Yeah, that's one point. Obviously, true, true. Or let's say I'm trying to not go about all those near about particles which are closer to the gas particle walls, just in between particles. So just think about that they are not colliding with each other, and then the with the wall. So how let's think about this situation, and now just think about how will there be any velocity distributions or not? Yeah, temperature is there. Yeah. Yes. Yes. So like this velocity now. Okay. Before commenting on that, now what is the reason for that? What do you think? If you say no, what is the reason for that? What do you think? Yes. 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 So basically, what we will say, the collisions between these particles, which are due to the temperature or the thermal agitation, these are the source of this velocity, right? They are colliding with each other. That's why this velocity emerges. Yes, that creates a distribution because in the previous thing, okay, someone joins, I guess. No, I shared a jam file with the meeting. I shared a jam file. Pranjal? Hello?
Hello.
Yeah, you want to say something?
No.
Oh, you have shared some file. I can see some Jamboard. Okay. If you have any question? Hello. Yeah, tell me. This one or this one? Okay, just a minute. This one or this one? Okay. Yes. Yes. Ye- Yes. 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 Excellent. You are absolutely right. You are absolutely right. That is that we are. I was just saying, and Tothagato was discussing about it. You are absolutely right. So this since these collisions are the sources of the the velocity distributions, and we will later see that this velocity distribution or this velocity are the source of the kinetic energy, because if they are moving, they have that kinetic energy, right? So from that perspective, we can say that if the collisions is stopped, we will not see the velocity distributions, right, Tathagata? Yeah, that we thought, right? We discussed, right? Yeah. So okay, so understand this point, and then if you have any questions, we'll we'll again talk about it. So as I have said earlier, so these collisions are the kinetic energy source, and so if the collision stopped, the velocity, which are the effect of this kinetic energy, will not be there, obviously. The distributions, which are the effect of these collisions, will not be there. Okay, think about it. Try to learn it, understand it, and then for 1 minute, then we jump into the next problem. Okay, any question, Pranjal, or any? I think we can hop into the next question, right? Yes. Okay. 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 So here, this says that formula for average velocity of a gas molecule with mass m at temperature T is this. So, any of you who wants to answer, like, what will be your guess? Because we are discussing, right? I want to get your response, then I will solve it. Obviously, I want to get your understanding, because I want to make sure that your logics and your reasons that you are giving here and your concepts will be it's right to solve this problem. Then we'll come to the mathematics or understand. So what is your comment, Tathagato, Panjal, any of you? Okay, okay. Pranjal? Okay, but I want to, like, what is, like, you are saying here velocity means velocity, or velocity means some other thing? Velocity means velocity, right? It has direction and all those stuff, right? So here you are talking about velocity means this has direction also, right? That we want to clarify at first. Either the point is of a gas molecule, right? The problem says that formula for average velocity of a gas molecule. So if that direction is there, so it's a vector quantity is there, and there is a distributions. So what do you think, that velocity should be positive, or the velocity is zero, or some average velocity is zero, or some value should be there? Is it? But let's say from a vector point of view, this particle is, since it's colliding, there will be a probability of going in this direction, or some finite probability, and in this direction some from a finite probability. And this probability are, since these are not a biased problem from statistical point of view or some probabilistic point of view, so there will be equal chance of going in this direction and equal chance of going in this direction. So from velocity point of view, are you sure that it would be root over of 8 RT by pi m? Exactly, that is why, that is my point. So if you are talking about velocity here, which has direction, and which has, magnitude also, then this should be averaged out to be zero. This should be zero. But if you listen to Professor Arnab Mukherjee's class, there he has actually clarified it, that from now onwards, whenever he is saying this is velocity, he will talk about speed, because he is talking about one dimension. Yeah, only magnitude. So, but I have just said you one thing. So from question point of view, this should be clear. If velocity means velocity, then that is zero, should be zero. But if since we have a reference lecture where he has clarified it, then we have to take a speed, and we will do the calculations in due course of time. But for, if it is velocity, then it should be zero, right? Tathagato and Tathagato is agreeing with me, I guess. Pranjal, it is Pranjal. Hi, Pranjal. Okay, 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 okay. ठीक है, ठीक. Okay. Okay, so okay, so come to this. So let's just comment here for velocity, which has direction taken into account, then average velocity is zero. But if only magnitude Good. Then okay, then we'll do the calculations. Okay, so probably you know the distributions, right? Velocity distributions. Maximum. This is 4 pi. Let me write it. 4 pi v square. There is a constant m by pi kb t 3 by 2, and there is a Gaussian kind of thing. kb t. Now this is rho v. So you probably know from statistical. Do you know any statistics or some kind of thing? If there is a distributions and you want to take the average of that, then that variable will be like that variable value and that frequency, and you take the average of that, right? That is the way of that. So from this point of view, v, which is average, this should be, so since it is only speed, it will be only positive 0 to infinity, and this will be right Tatagato. Yeah, this will be v rho v dv, right? This we know, this is the integral form. So now this v, we will take all the constant part outside. So this will be 4 pi by 2, 0 to infinity. So there is a v, and here there is a v square, right? So, so this will be v, sorry, this will be v cube, and it will be exponential minus m square by 2 kbt dv. This is a standard integral, which is actually a gamma integral, it calls. So let me solve it, because yes, so I'm just writing the formula because this will be useful. So this is called 0 to infinity. If it is, let's use another variable. Okay, that would be x to the power n e to the power minus alpha x square dx. We can say half into gamma of n plus 1 by 2 into alpha to the power minus n plus 1 by 2. You have probably seen, there is, if there is minus infinity to infinity, then there will be 2 times of this. Okay, only this thing. Even for even function, for odd function this will be exactly, and that is actually the concept of speed, velocity. So if that should be exactly right. Yeah, so now this is the thing, and if we put this thing together, then this will be 4 pi as usual m by 2 pi kbt by 3 by 2 times. So half will be half, So this is n equal to 3. So then this will be gamma 2. And what is the gamma 2 value? So what is the gamma 2 value? You know? Okay, okay, no problem, no problem. So gamma n is equal to n minus 1 factorial. Okay, n minus 1 factorial. So gamma 2 means 1 factorial, that means it's 1, right? And this alpha means this whole thing m by 2 kbt is alpha. If you compare these two term, this one and uh, this one. So this m by 2 kbt by same thing n plus 1 and 3 plus 1 is equal to 4 by 2 minus 2. So this will be minus 2 here. Now this there is one m by 2 kbt to the power 3 by 2, this m by 2 kbt minus 2. So this will be m, let's m by 2 kbt minus half. Okay, this 2 and this 4, this 2 and 4, this will be 2. So this will be 2 pi, and this will be, there will be 1 pi left, 1 pi 3 by 2. So 1 pi will be cancel out, and from here, yes, this will be 2 kbt. So let's input all these things. This pi will be there, this pi and m all will be half into 1 2, that will remain, right? These two. So this, if we intake these two into the bracket, this will be 4. So 4 into 2 means 8 kbt by pi m. Okay, so here the thing is, this is for one particle, but here is gas molecule with mass m, they have said, and the options should be 8 kbt by pi m. But since I think there will be a if it is a mole, number of mole, 1 mole of gas molecule, then it would be this one. So then this would be same. Actually the answer should be 8 kbt by pi m, okay, to the power half. So if there is 1 mole of that, because R is Avogadro number n into kb. This is Boltzmann constant. Okay, right?
Yes.
Okay, okay. So any problems, Pranjal? Yeah. So you want me to what you want me to do? Okay. Will be taken. Okay. Yeah, sure. So okay, so here what we have said for velocity, if when we take into consideration the direction, then that should have equal probability in the minus in both directions. So that will cancel out each other, and that will average out to be a 0. But if we take magnitude, as Professor Arnab Mukherjee has said in his lecture, that here onwards all the velocity thing will be taken into as speed. So then we have to calculate the average speed. So for that we need to know about this distributions of these gas molecules, which is a special kind of gas molecule distributions, which called, let's go to the tab, which called these distributions called Maxwell as তথাগত commented on this, that this is Maxwell Boltzmann distributions. And then if we have to calculate the average of that velocity, then that should be average of that quantity and the distributions of that quantity which I want to calculate the average of. And then we have to integrate out. And then we have done this integration where this constant part 4 pi, this all this constant and I have taken into account, taken outside. And since there is v square, there is uh, v square, and there is v, that should be v cube, and this will be exponential of minus mv square by 2 gravity. And if we do the integration, this is a standard gamma integral which has the form x to the power n e to the power minus alpha x square dx. This has this standard value, and if it is for like total integral minus infinity to infinity, for odd function it will be 0, for even function there will be twice of that. Now after putting all those values, we get this thing, and will do some algebra that I will not go into the details because it's quite simple. And that should be answer would be 8 kBt by pi m. For one molecule, kb is Boltzmann's constant, but if it's for 1 mole, this should be r, which is related as this Avogadro number Na times kb, and that should be the option. So no, you just right now it is clear, right, Pranjal? Clear, right, Pranjal?
Yes.
Yeah, yeah. Okay, thank you. Okay, let's go to the next problem. Okay, now this problem states I calculated the root mean square speed RMS of helium and krypton gases at temperature T. My calculation shows that RMS for both gases is same. Is my calculation correct? First option says yes, since the temperatures of both gases are same, the RMS also will be same. Second option says no, even though the temperature is same, masses are different, and that will give different RMS. Okay, so we can do this problem when we know about root mean square speed, right? So I think the next problem talks about root mean square speed. This problem. So we'll actually do this problem first, and then we'll come to the problem number 7. So this problem number 8 actually we will do first. Okay, Tadagato? Because this problem number 7 actually we can do when we will solve the problem number 9. There is root mean square speed. Okay. Okay, so we will do this problem, small problem. What will be the pressure of two cylinders containing same number of helium and xenon gases at same temperature and volume? So the pressure of helium cylinder will be more. Both cylinder will have the same pressure. Pressure of xenon cylinder will be more because xenon is heavier than helium. None of the above. Now, Tathagatha, what is your comment on this?
Same.
Same pressure. Why is that? Exactly. Fantastic. Fantastic. Precisely. So, as Tathagata said, that we know the equation of state, right? This is called equation of state. PV is equal to N R T. This is the equation of state, right? For ideal gas. Tathagata? Hello. This is equation of state, right? So they have the same volume, same temperature, and this is a constant value that doesn't depend on the what kind of gas we are taking into account, but that should be ideal, of course. And this is the number of moles that would be the same actually, because they said that's containing same number of helium. So if this all the right hand sides are same and also the V also same, then both cylinders, the answer should be both cylinders will have the same pressure. Okay. Okay, so this is option number, this one. Okay. Let's go to problem number 9. Okay. So problem number 9 says this is a typo. This is root. Okay. Root mean square velocity of a gas with mass m at temperature T. Now, what is root mean square at first? Let's say as root mean square. As the name suggests, we'll take the mean of these, because we'll take the variable square and then we will take the average of this. Then what we will do? We will take the this is right, square root of that. So, but we have to calculate this one first. This v square average. So, from the previous thing we can do, right? Previous, because this is mathematics. From previous thing. Exactly. Here also the velocity means this uh, same thing like the speed. Also, yeah. So let's write this rho v 4 pi v square m by 2 pi k b t to the power 3 by 2 exponential of minus v square by sorry v square by 2 kbt. So you guys can see my like when I'm writing in pen, you can see, right? Yeah. Thank you. So then v square average will be 0, same 0 to infinity v, v square rho v dv. Okay, and if we put all the expressions, then v square equals to 0 to, let's okay, let's take out all the constant. Okay, 4 pi 2 pi kbt 3 by 2. Okay, then this will be 0 to infinity v to the power 4 exponential minus mv square by 2 kbt dv. Now same thing, gamma integral 0 to v x to the power n with the power minus alpha x square dx half gamma n plus 1 by 2 alpha to the power minus n plus 1 by 2. Okay, so what will be the thing? This will be 4 pi m by 2 pi kbt. This is v to the power 4, so there will be half ones. Sorry, and this will be 4 means root over 5 by 2. So this will be 3 by 2. Sorry, 3 by 2 half and root pi. Gamma half is root pi. You know that, right? Gamma half is root pi. Because yes. So this will be like this. And if we put this here, this is 3 by 4 and root pi, and alpha means this m by 2 kbt, this will be minus 5 by 2. So this okay, this 4 and 4 cancel out, this root pi and root pi will be also cancel out, there will be no root pi. Okay, so if you do the calculations, then there should be, this should be m, sorry, m by 3, okay, m by 3 k b t. Okay, how this is? So this 2, this 4 cancel out. Okay, and there is 2 3 by 2, and there is 2, and that makes 2 to the power 5 by 2, and there is 2 to the power minus 5 by 2, that will cancel out. There is pi also cancel out, because this is pi and this is root pi, this is pi to the power 3 by 2, and there is pi to the power 3 by 2 in the in the denominator, that will cancel out. So there will be one m here will survive, 1 kbt will survive, because 3 by 2 minus 5 by 2 will be minus half, minus 1. So that will actually we will we will that here this will be 1 minus 1, because this m kbt and this 3, that will actually reverse that. Sorry, yeah, we will reverse that. And same, yeah, this thing we will see 3 kbt by m, because you can see, right, this is this kbt, and this 3, if we take it here, this is 3 kbt, and there will be minus 1. This is clear, this calculation clear, right? Yes. So this is for one molecule, but for a gas, say, no, this is actually, yeah, you are right, but this is for v square, right? We have to take the root. Yes. Then for 1 mole means Avogadro number of molecules, this should be v square average should be 3 RT by M, because you have earlier seen that R is Na times Kb. So what will be RMS then? RMS, let's say subscript VRMS, which is root over of v square. This will be root over of 3 RT by M, or M, whatever the function is. Okay, so this is the option, right? First option. Yeah. Okay, now come to the Pranjal, any questions so far? Okay, thank you. Okay, okay. Let's come to this question. So here it is, if I read correctly, I calculated the root mean square speed of the helium krypton gases at temperature T. My calculation shows that RMS for both gases is same. Is my calculations correct? Yes, since the temperature of both gases are same, the RMS will also be same. No, even though the temperature is same, masses are different, that will give different RMS. Now I have calculated the thing. So any of you with some guess, or with some, I think you shouldn't have guessed it. You have probably got the answer. Yeah, option B. So okay. So here we, as we know, V RMS is equal to 3 RT by M, or M. So they have different mass because they have different molecular weight. Krypton and helium number, they have different molecular weight or atomic weight, whatever, because they're periodic table, they're in different. They do not have the same number of protons, electrons, and you can talk about that, right? They do not have the same mass. They have same temperature, so masses are different. That will give different RMS, right? Masses are different. Okay. So I want you guys to look into these solutions and tell me one thing. This solution is hectic, right? It's quite tidy. I mean, it's quite laborious, tedious. You have to do a lot of calculations, lot of integrations, right? Totakato, Panjal, tedious. Okay, so if time permits today, I will give you a good from physics point of view, from physical point of view, a good argument, so that you whenever you always calculate this RMS, you can always calculate the RMS speed pretty quickly. Okay, so I'll talk about that. Okay, so hold on, we'll talk about it, but later I have to finish all the problem. Okay, the last problem. Most probable velocity of a gas with mass m at temperature T will be first option root over of 3RT by m, 2RT by m, root over of RT or root over of T by m. Your guess, or you have done it, or you have done it earlier, something like this. Your guess. Root over 2RT by m. Nice guess. So how can you do this? How are you going to do this? So okay, so infinity from which perspective? There will be an exponential, right? Okay, so I think infinity velocity is some kind of unphysical. It doesn't have any physical sense, and zero means like it's quite in. It is just it is like do not have any motion. So that, yeah, that's also the thing. Okay, so you have excellent. You have said it correctly. Now we will solve it. Okay. So as you have rightly said, Tothagato, that this we will know the Maxwell-Boltzmann distributions, which is 4 pi. Again, I am writing this because whenever I am writing this, it will be a good practice. You will also write it, and then this formula will be actually, you will always feel easier to remember the formula. Anyway, this is, I always forget this formula. But anyway, the formula is not actual thing. To have to understand, you have to understand the physics behind it or the science behind it. Okay, so most probable velocity means for this function, for which value of v, this rho v is maximum, right? Are you able to follow my arguments? Most probable velocity means for which velocity this curve or this function is maximum, right? Now, for that, for a maxima, we know del rho del v should be 0 because it is extremum point. For a maxima or for a minima, the slope is always 0. That is the concept. Okay, so that is thing. On top of that, as you know, for del 2 rho del v2, that needs to be less than 0 to suffice it that it is the maximum, isn't it? So the logic you have given, this is perfect, but we have to for the complete to complete the argument, we have to give this argument also. Okay, we will see that. Sorry. Del rho del v equal to 0. That brings to, I will ignore all the constant part. Okay, so because this is, let's say, constant part is like a star, because that doesn't count to the differential. This is 2v exponential, let's say I'm calling this m by 2 cavity also alpha v square, and then again minus, sorry, minus mv by kbt into v, okay, right? Let's say this is alpha, I called it. This is alpha, this is 0. Okay, so for this, let's say, exponential term, I'm taking it as common. So out of this bracket, so this will be 2v minus mv square by kbt. And this v is a special v. This is v star. This v star means for this to be 0, then it is a extremum point. We will not call it maximum or minimum. This is a extremum. It calls extremum. When the slopes of a curve is 0, it called extremum. Okay. So for this v star set of values, this is 0. So we can say v is infinity. For that, it can be 0 because this is exponential curve. So this is unphysical. Or from this thing, if we take common v, then 2 minus mv by kbt. So from here we can say v equal to 0, okay, or v equal to 2 kbt, oh, 2 kbt by m. I have somewhere done wrong. Okay, I got it. This should be v square, right? Because this is differential of this and v square of is there, so this will be cube, and this is v square, so this is so this is v square. No, I'm talking about this. I took it as v because this should be v square, because yeah. I understand what you want to want to mean it. What you, this is like, if keeping v square constant, you are differentiating this. Yeah. So this is v square is this. So now it is pretty straightforward. This is most probable. This is 2 kbt by m. It is the answer. And also, like the same argument, I'm not writing it again. This will be this one, right? This one. Okay. Now I haven't finished my argument. Okay. Let's say if you put v equal to 0, then this will be 0, right? This term will be 0. This term will be 0. So that doesn't say about this thing. So this cannot be the most probable velocity, because yes, right. This is right. Yes. And now if you put infinity, that is also 0. Now if you put this one, where is this? If you put this one, what should be the case? What should be the case? Hmm. 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 So that is also not less than zero. So yeah. So what we can say that it is from maximum point of view, we can say this del 2 rho del v2 is greater than zero, right? So does it matching this thread of logics matching with that according to the thing? Yeah. So but here so for here the most probable velocity by this they want to mean that what is the extremum point, because anyway the at probability cannot be negative, right?
Yes.
So that point of view what they wanted to see that at that velocity v star is root over 2 kbt by m, or we can see like we have to again differentiate that del 2 rho del v2 where this is that I am giving you a homework. You can do this homework. So you have to check here. You have to take double derivative of this. So you have to just differentiate it once more. Okay, this expression, and then you have to put this v star value root over of kbt by m. And if that is less than zero, then you can say this is maximum. Can you do this? You can try, right? It's pretty simple, yes. And then you can see that for that value, it is actually happening. That is actually maximum. Okay.
Okay.
So just think about it. I'm just taking. Just think about 1 minute. I'm just taking a sip of water. Okay. Okay. So you can do the differentiation once again and then put the register value and you can get the all the other things. Right? Totagato?
Yes, sir.
Yeah. No, don't call me sir, okay? You can call me Dibyendu or Dibyendu Da or something like that. Okay. Okay. So this is done. So now I have added some further problems which were there in a non-graded problem. So we'll talk about that. And in this problem, these problems actually will help you to understand one more concept which is called extensive property, intensive property. I will actually I will clear the concepts and I will help you to solve those. Only I will not complete. I will not help you to I will not give you the solution of the this year this semesters or this year assignments that we will do. But I will actually clear your concept that will actually essentially help you to solve the assignments. That's for sure. That's for sure. That you can do because always it is being graded to all. So the concept should be understood, right? Tathagata?
Exactly.
Exactly. Concept should be. We should discuss about these things. We should debate with each other that this is not right or this is wrong with valid reasons. Obviously, valid reasons. and that basic, the stairs of logic should be there to follow for any kind of claims. Okay, so let's just take this question. Okay, so this question says that for which system neither heat nor matter can be transferred across the boundary, select the correct one. So, any comment, Tathagoto? Quick comment.
Isolated.
Isolated system, right? So, yeah, yeah. Thank you, Pranjal. So, for there are open. Open means matter and energy all can be transferred, right? Close means energy can be transferred, right? Matter
Yes, sir.
for isolated. This is for isolated. It would be neither matter nor energy. Okay, so this is the answer. Okay, is this clear? Can I go to the next problem? Yeah. So this problem says zeroth law of thermodynamics deals with conversion of mass and energy, deals with reversibility and irreversibility of processes, state that if two systems each are in equilibrium with third system, then they are thermal equilibrium with each other. So I think this one, because we have discussed about zeroth law of thermodynamics in detail, Tathagato, in the first half. Yes, in detail. So that that is the answer, self-explanatory. So for Pranjal, do you understand this point, or I have to?
Yes.
So let for Pranjal, since he was not there, so there will be three system A, B, C. So these are in thermal equilibrium, and they are also thermal equilibrium. So that means that they are also in thermal equilibrium, right? That is called equivalence principle also. So one information, zeroth, sorry, law of thermo, sorry, sorry, okay, zeroth law of thermodynamics is equivalence relation. Okay, let's go to the next point. Kinetics theory of gases assumes that collisions between the molecules are. This is a pretty simple problem. Follow?
Yeah.
Yeah,
Perfect.
yeah, because these are ideal gases. So just write one point. Ideal gases. That means no dissipation, right? They do not dissipate, right? So that means perfectly elastic. Okay. Now I will take some time for this problem. This problem, the statement of the problem is pressure is an extensive property, true or false? Now, any of you who knows about what is extensive property or intensive property? You know, or I will talk about it. And
Extensive.
okay, so I didn't understand your point. So you are saying that extensive property or intensive property is some kind of on the system by the system. I just please one more. So I didn't like there's some breaking of the voice. Okay, okay, I understand. So work done by the system is intensive, and work done on the system is extensive. That you want to do, right? Yes. So just one thing. Okay. So for you, so how can you say? What do you say about this? So color of a system. This is extensive or intensive? Ranjan. Okay. 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 So, so Sagato, do you want to try? Why is so? Yeah. Yeah, 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 yeah. You are correct. You are correct. Okay, just yeah. I'm probably Pranjal. You are probably somehow mixing these two, some path dependent function or some kind of state dependent state function, path function, some kind of thing. So this sort of different actually. So this is property actually, not function. Okay. So what you had said it quite interesting, but I think for intensivity or extensibility of the property of some system, we have to define it like this: is property. Sorry. Property changes when the size or extent of the system changes. Okay, this is called extensive. If does not, intensive. So so here, if size of the system changes or extent of the system changes, let's say it is in the like, that means like all of the system well, means the system size is changing proportionally, but then pressure should be changing or not? Not, right? This is a false thing, because there is x gram of x gram of molecules in v volume, and if you 2x, if you double it, then there will be 2x volume, 2v volume, and 2x amount of molecules. So that pressure will be always same. So I will give some variable or observables, and you have to say whether it is extensive or intensive. Let's say temperature, intensive. Pranjal, viscosity, Pranjal. Yes, yes, precisely, 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 intensity. And let's say enthalpy. Ah, enthalpy. Any kind of free energies, enthalpy, Helmholtz, Helmholtz, free energy, and then Gibbs free energy, Gibbs free energy. All, sorry, they are all extensive. One interesting thing, all the specific gravity, specific density, specific heat, well, they are all intensive, because they are getting like the system, that doesn't depend on the extent of the system, because that will be mass by volume, volume by mass, or heat capacity per volume, something like that, right? So these things all will be intensive. Intensive, is there any property? I didn't understand, I didn't hear you properly. Yeah. So specific heat, like heat actually is extensive, right? But when you are taking by volume, that is specific heat, then you are talking about intensive property. So for extensive property, so there will be ratios, because density, so mass, so ha, exactly, mass, volume, they are all extensive, but density, which is m by v, is intensive. Okay, so it's understandable, I guess. I think if you do this thing, I have given enough examples. You can solve the assignment problems also. There are also some problems there, so you can solve it. So refractive index, this is intensive or extensive? Just for a small problems. Refractive, uh, re- refractive refractive index. Yeah, yeah. Yeah. You're in right track. Yeah, great. Yeah. Okay, the last problem. Let's say you have two glasses of 5 ml water. The temperature of one glass is 350 Kelvin and temperature of other glass water is 330 Kelvin. Now you mix the water would be the final temperature, something like this. So what would be the simple answer? Yeah, 340. Yeah, this is simple because this is CW and T1. Okay, yeah, CW T2 will be C final T. Since CW are same and CF is also same, so this CW T1 plus T2 and this is also okay. So there will be volume element also. Volume element. Yeah. Hmm. So this will be 350 and 330. This is sorry. CW cancel out. This will be 350 plus 330 is equal to 2 into T. V cancel out. V cancel out. So T will be 680. This will be 340. That's the answer. Okay, that's the answer. That's the thing. But I have one thing left for you. I talked about it that if time permits. So since it is, I can take only 4 or 5 minutes for that. So do you agree to? Okay. Okay. So I said that there are another way to talk about the RMS speed. Okay. So when you're talking about the molecular fluctuations, the atomic fluctuations, so there is nothing mean or something like that. We always talk about our RMS. RMS. That actually maps the energy per degrees of freedom. Okay. So there is a good theorem. This is called Sorry. Have you heard about this equipartition theorem?
Yes, sir.
Yeah. This is called equipartition theorem. It tells that for each degrees of freedom, there is a half cavity of energy. So for velocity here, sir meant to say this is for three-dimensional, right? That's why that three-dimensional object or system. That's why that 4 pi comes in the distribution. When you take the solid angle and you take the conical shape, because when you are talking about the this thing, the conical shape, this 4 pi comes solid angles. If you know about the distributions, the calculation of the distributions. So here we talk about RMS speed of three-dimensional speed, not a one-dimensional speed. Okay.
Yes.
Okay. So for if for one degrees of freedom it is half cavity, for 3 dimension, for 3 degrees of freedom, what will be the 3/2 cavity? Okay. For this. Okay. Now, as we know, Vx square plus Vy square and Vz square is equal to V square. And this is the kinetic energy for the degrees of freedom. Okay. So for half of that will be half m of Vx square, Vy square, Vz square. That will be this, right? This will be this. So if we substitute this thing, then this comes V square by 2. So 1 3 by kBt, and this will be by m. That turns me into V square, which is average, because this will be all the this all be RMS, because RMS is only responsible for the kinetic energy. So this will be 3 kBt by for one particle. If it is for Avogadro number particle, this will be 3 RT by n. This proof
Exactly.
this proof is quite simple, right?
Yes.
Yes. So that's a
Yes.
different angle, different partition theorem. If time permits, I think in the later lessons there is enough scope for equipartition theorem discussions. So I will just quickly talk about the just a minute. Let me save it. Yes, all slides. Control S. All slides. Okay. Okay, just I will do it later. Okay. Let me just summarize the concept. So we first talk about zeroth law of thermodynamics, and this zeroth law of thermodynamics follows two basic properties, which is reflexive property and which is Euclidean property. And to be precise, I will not go into the details. This is called left Euclidean. So it is quite mathematical term, left Euclidean. So if a binary relation is reflexive, and also Euclidean, then that is actually equivalence relation that I have discussed, right, in this way. Now, since this is equivalence relation, we can actually compare those systems which are in thermal equilibrium. That's why zeroth law of thermodynamics talks about a variable which can be compared, which can be tagged to all the systems which are in thermal equilibrium. And we later actually from phenomenologically phenomenologically way we know that it is temperature. We assign that we define that variable as temperature. And one important point for zeroth law of thermodynamics is it talks about temperature without mentioning the name of entropy once. So that's one thing. And here the concept of temperature is purely macroscopic. Here we will not talk about a microscopic thing. That's why in a volume of in a volume of V, for all the molecules the temperatures are same. That's why here for zeroth law of thermodynamics, temperature is a macroscopic concept. Sorry. So we have done this, and Ralph Flower has established this thing. And then we have talked about collisions and their specific distributions of the velocities, and the RMS speed 3 root over 3 RT by m, and again here the average speed, which is 8 kBt by pi m, the root over of that. And for if we talk about velocity, which has directions, that should be 0. And we have calculated RMS with different method also, equipartition and also from the distributions. And later we understand about extensive and intensive properties, right? This is our this thing, right?
Yes.
So that's the thing. Okay, just wait for a few minutes. I will stop recording.